very small topic is left, which is ideal diode characteristics graph. The graph of ideal diode is very simple, which actually look like mirror image of English alphabet L. The graph lies on negative voltage axis and positive current axis. From the graph you can see that the cut-in voltage is equal to 0, and when the voltage is greater than cut-in voltage, then the current passing through the diode is infinite, and when the voltage is smaller than or equal to cut-in voltage, then the current is equal to 0. You can also see that there are no reverse breakdown mechanism in the ideal diode. Now we will summarize all the lectures which we have covered in this unit. Initially we studied what is depletion region, and we got to know that when a semiconductor is doped with p-type material in one region and n-type material in other part, then a depletion layer is constructed at the boundary where the p-type and n-type material are doped. And after that, we discussed few approximations which we usually assume in the whole chapter so that it is easier to derive the formulas. Like, one approximation is depletion layer approximation, in which we assume all the dopant atoms in the depletion region, whether donor or acceptor, are completely ionized. We also assume that in the neutral p-type and n-type region, electric field is equal to 0. Also, potential is constant. After that, we studied the contact potential, in which we got to know that even though the neutral N and P region are having constant potential, but still there is a difference between their potentials, which is called contact potential. And we also derived the formula which is equal to KTYQ into natural logarithm of Na into Nd divided by Ni square. We actually derived another formula for contact potential which is equal to After that, we analyzed few important parameters like electric field, potential difference, and the length of depletion width. For reference, we took the simplest concentration profile, which is step graded junction. We got few very important formulas, one of which is this relation. Also, we can write the formula for maximum electric field to be equal to and this formula is also particularly valid for step graded junction. You should remember all the formulas for step graded junction, as generally questions based on step graded junction are asked. So it will save a lot of your time if you remember the formulas. And the very important thing that you should keep in mind that the initial units like the basic semiconductor physics, which is the first unit, this unit which is the PN junction and Zener diode, and the next unit which is going to be optical devices, all these three units are actually interconnected. So it is not difficult to understand the topics separately, but it is going to be a challenging task for you to actually connect different topics from different units. In the first unit, we studied Poisson equation, but questions which are entirely based on Poisson equation are never asked. However, if you remember the derivation for electric field, then you might recall that the first step that is required for deriving the electric field comes from Poisson equation. And after getting the electric field, you can derive the potential difference. Basically, all the formulas which we have studied for the step graded junction or linearly graded junction, Poisson equation is actually the basic equation from which we have to derive all the equations. After deriving formulas for step graded junction, we moved to linearly graded junction. There is no need to remember the formulas, as there can be a different concentration profile than linearly graded junction. If you understand the derivations, then you can derive formula for any concentration profile. Otherwise, it is going to be very difficult for you to remember the formulas for different possible concentration profiles. We also derived the formula for depletion width, which is equal to this formula along with ideal diode current equation are the most important formulas in this unit. After that, we studied biasing and energy band diagram. Biasing simply means applying external voltage. If we apply positive voltage on the P side, then it is forward biasing. if negative terminal of the battery is applied on the P side, then it is reverse biasing. Otherwise, if there is no battery connected, then it is called zero biasing. We also studied that when we apply biasing, then there are slight changes in the energy band diagram, and the difference in the conduction band energy levels in the p-type and n-type region is equal to Q into V0 minus Vf. We can also write Vf equal to minus Vr such that the difference will become Q into V0 plus Vr. Here Q is charge on an electron, which is negative. In different topics, it may be possible the same symbol can represent two different parameters. They might be similar but not exactly the same. Like here in the formula for depletion width, this is absolute charge on an electron. However, here in this equation, this is the charge of an electron. It might be a little bit confusing, but if you are having good knowledge of the subject, then it will become very easy for you to determine which parameter is actually being represented by particular symbol. So, while you revise the chapter, then make sure that you are clear about which parameter is being represented by Q in different topics of the unit. Also, when we apply biasing or an external voltage, then the formulas are also changed. Like for the depletion width formula, the formula changes to simply for biasing, you have to replace V0 with V0 plus VR, or in forward bias condition, you have to replace V0 with V0 minus Vf. After that, we studied the ideal diode current equation, which is here I0 is called reverse saturation current, whose value is equal to you can see that reverse saturation current is actually dependent upon the area of cross section, and that's why it is also referred as scale current. Its derivation is very long, but the most important point in this derivation is that we actually focus on minority carriers, even though the majority carrier concentration is significantly greater than minority carrier concentration. And to understand why this is so, you have to go through the first unit where we studied ambipolar transport equation. Questions are usually not framed from this topic, but still I taught you because I know this lecture is going to help you to understand why minority carriers are taken. As when we were studying ambipolar transport equation, then we concluded that effective diffusion constant as well as the effective mobility, when there is a significant difference between the majority carrier concentration and minority carrier concentration, then the parameters are actually dependent upon minority carriers. I have already told you that the most important unit is the first unit, and I am again telling you that for understanding the further units, it is very important that each and every topic which you have studied in the first unit is crystal clear to you. When we derived the equation for ideal diode current, then you should recall that why it is actually called ideal. This is called ideal because we have considered Shockley ideal diode approximation, according to which in the transition region there is no recombination taking place. However, for a practical diode, that is obviously not true. To include the effect of recombination, we slightly change the net current equation by introducing ideality factor n. After that we studied, it is not true that we can apply reverse bias voltage without any limit. If we apply very high reverse bias voltage, then junction breakdown mechanism occurs, as per which the current increases very sharply even for a small increase in voltage. The two breakdown mechanisms are Zener breakdown and avalanche breakdown. Zener breakdown occurs due to tunneling mechanism, and avalanche breakdown occurs due to impact ionization. The avalanche breakdown voltage is significantly greater than Zener breakdown voltage. We also studied that suppose if we have a semiconductor in equilibrium having one Fermi energy level, and if we introduce excess charge carriers delta n or delta p, then the Fermi energy level gets split into two parts EFN and EFP. These two Fermi energy levels EFN and EFP are quasi-Fermi energy levels. After studying so many concepts, we finally constructed the graph for voltage current characteristics of a diode. And in the graph, we introduced another parameter which is cut-in voltage, which is defined as the reference voltage above which the current increases very sharply. Another parameter which we defined from the graph is GD, which is called incremental conductance, which is the slope of the graph, which comes out to be equal to approximately current passing through the junction divided by ideality factor into thermal voltage. The exact expression for incremental conductance is I plus I naught divided by ideality factor into thermal voltage. When we apply sufficient voltage, then the current I is significantly greater than reverse saturation current I naught. That's why we usually ignore the term I naught. Another parameter which we define from the graph is RD, which is incremental resistance equal to the inverse of incremental conductance. We also discussed depletion capacitance and diffusion capacitance. Depletion capacitance is represented by Cj and is having other names like junction capacitance and transition capacitance, which is equal to where alpha is equal to. Similarly, the formula for diffusion capacitance comes out tau, which is the average of minority carrier lifetime multiplied by the current passing through a junction divided by ideality factor multiplied by thermal voltage. After getting so many parameters, we defined an equivalent model in which we represent diffusion resistance, junction capacitance, diffusion capacitance, and sometimes we also represent another resistance Rs, which represents the resistance offered by the neutral N and P regions. Xenon diode is a highly doped PN junction such that the breakdown occurs at low voltage. Xenon diode is operated in reverse bias condition. However, if we forward bias a xenon diode, then it will act as a simple diode. The avalanche breakdown is a predominant breakdown mechanism in a simple diode. So, if we want the semiconductor to have Zener breakdown mechanism to be a dominant breakdown mechanism in a diode, then we have to dope the semiconductor with high concentration of dopant. Our second unit PN junction is now finished. Our next unit is optical devices, in which we are going to discuss 4 devices which are photodiode, solar cell, light emitting diode and laser.